So in today's class, we shall be starting with the continuous distributions. In the last session, we had covered all the major standard discrete distributions, be it the form of their probability functions, be it the calculation of their mean or variances, as well as their applications. Further, we also took a look at what sort of values have been given in actuarial tables, be it the form of the probability function for these distributions, as well as the values for the cumulative probabilities for Poisson distribution as well as binomial distribution. So in today's class, we shall be covering, let's see how many continuous distributions. We might not be able to cover all of them in today's class, but a major chunk of these we should be completing in today's class. As compared to discrete distributions, the number of standard continuous distributions which we would be studying is going to be far more. Also, I would be covering certain distributions which haven't really come that frequently in CS1, but they do come in CS2. So for completeness, I would be touching upon those distributions as well. Again, the underlying concepts, everything remains same. It's nothing new which we are gonna do. So just that you wouldn't really find a lot of questions, maybe asking you about Pareto distribution or Weibull distribution, but these are something which are going to be tested in a lot more detail in CS2. So we would be completing this today itself. So first, let us take a list of the distributions which we are going to study, starting with uniform distribution. First is the uniform. Next, we will take a look at exponential. Next, we will take a look at gamma distribution, then Pareto. Then we will also take a look at general Pareto, or how should I write it? 3-parameter Pareto distribution. Next, we will take a look at Weibull. We will also take a look at beta. Then we have chi-square. Then we have the all-important normal distribution. Then we have log normal. Then we have the t distribution, and we also have the f distribution. Again, keep in mind there are a lot more standard continuous distributions, but these are the major ones which are there in our actual curriculum. Leaving, let's say, Weibull distribution, 3-parameter Pareto, and Pareto distribution, and beta distribution, all the other ones are extensively used in CS1. Specifically, exponential, gamma, normal, log normal, t, f, chi-square. In later chapters, when we start with, say, confidence interval, hypothesis testing, so on, we will see the importance of t distribution, f distribution, normal distribution, as well as chi-square distribution, be it with respect to its form, its application, how to calculate probabilities for same, and so on. So these are the ones. Let us see how many we are able to cover in today's session. So first, give the heading uniform distribution. Now the concept remains the same as we had in case of a discrete distribution. when we were studying uniform discrete distribution, we used to model it in the scenario when all the possible outcomes were equally likely in nature. Similar concept here is, note that in continuous there is no concept of probability at a single point. Here what we talk about is, let's say, PDF or the relative likelihood. So in uniform distribution, all the points are equally likely. So the PDF structure which I have, first let me write how do we express it. X follows uniform. A comma B, the parameters are A and B, where X can take the values between A and B. Again, keep in mind whether you put an equal to or not doesn't matter. It's a continuous distribution, so it's all the same only. And the PDF of this is nothing but 1 divided by B minus A. So you see that the PDF remains constant irrespective of the value of X. And the range, the values which X can take is between A to B. For example, if I tell you that you have been given a particular number line, okay, between 0 to 2, you need to put your pen on that particular line and then see which particular point you have put at. So it is equally likely that you might put anywhere between 0 to 2. So I can say model this as nothing but a uniform distribution over the interval 0 and 2. So here, how do you model? You need to first check what are the possible values which X can take. The lower limit will become A, the upper limit will become B. And if you feel that they are going to be equally likely in its entire interval, we can model it as a continuous uniform distribution. So this becomes my PDF. Along with PDF, we would also be focusing on CDF wherever possible. Now there is a terminology called closed form. Whether a CDF, cumulative distribution function, for any random variable or for any standard distribution, does it have a closed form or not? What do I mean by closed form? When we are being able to give a, let's say, a simple formula or a numeric, a single line formula for the CDF. In certain cases, there would be no general formula for CDF, but in a lot of cases, there would be a general formula for the CDF. Wherever the general form, that should be the more technical way to say, wherever a general form of CDF is available, we see it that the closed form of it exists. So what I mean by this is, first of all, the CDF of S is nothing but X minus A by B minus A. Again, we will be closely looking at how we have calculated this. For the time being, I'm just quoting the results. Expectation X is A plus B by 2. Variance X is B minus A whole square by 12. Now coming to it, how to go about performing integration of all the distributions. This one is the easiest. So if I want to start with CDF, if you would remember, CDF is nothing but integration of PDF from limits. In this case, the lower limit is nothing but A and the upper limit will be X. Integral Fs. What is Fs? 1 by B minus A, which is nothing but a constant. I can take it outside integral. So what I'm left with is this, and this is 1 by B minus A S A2X, which on simplifying will come out to be. Same thing you can do for mean and variance. Your mean will be what? Integration X Fx dx. Limits are from A to B. So you will directly have X, you need to square it, you will have X square by 2 and you can proceed on. So there is no sort of manipulation as such required whenever you're calculating, say, the expectation X or even the expectation of X square. Again, see, formula everywhere remains the same. My only emphasis is key for any particular distribution. Is there any particular technique or particular manipulation required while dealing with its integration? In case of uniform, that is not the case. So we are restricting ourselves right now to calculation of CDF only. You can give it a shot, calculation of the mean and variance, just to see that you are getting these values. Next, we have exponential distribution. The way we denote it is x follows exponential lambda, where lambda is strictly positive. PDF is given in the form lambda e to the power minus lambda x, where x is greater than 0. So focus on these things. First of all, when we were doing uniform, there was no restriction in the parameter. A could take any value, B could take any value. Just keep in mind, obviously the value of B will be greater than that of A. When we write it in this form, x is greater than A is less than B, it automatically implies that B is nothing but greater than A only. Here, there is a restriction on the choice of parameter value. It needs to be positive. Now coming to the range of PDF. In case of uniform, it was between A to B. Here it's going to be the set of positive numbers. That is between 0 to infinite. CDF. This will be 1 minus e to the power minus lambda x. Expectation x will come out to be as 1 by lambda. Variance x will come out to be 1 by lambda square. Just notice one thing, the variance x is given to be 1 by lambda square. So my standard deviation will be 1 by lambda. So if you'll observe, in case of exponential distribution, the mean and the standard distribution are same. So the application is, suppose when you would be studying the higher chapters later on, we will see we might have a data set. We would calculate its sample mean, sample variance, and then we would try to fit any particular distribution. So if we see that the mean and the standard deviation are very close, or let's say exactly same, exponential distributions could be the first distribution which you all should have in mind, because here the theoretical mean and standard deviation are same. So maybe later on, once we actually do the other chapters, precisely point estimation or hypothesis testing, there we need to see if we do not know what data, the data might come from which distribution, we need to fit a particular distribution. Then basis all these properties, the range of values, the value of the expectation variance, the relation between them, we can start with an initial guess, which distribution could be used to fit it. Whether it will be a good fit or not, we would be testing them again later. So this is just reiterating, try to see what each distribution, what might be similar, what might not be similar, and so on. Now let us take a look at how to go about performing integration in this case. If I start from CDF, this should be a fairly straightforward one. Integral fs ds 0 to x lambda e to the power minus lambda s ds 0 to x. Integration of this is nothing but minus e to the power minus lambda s 0 to x. And if I substitute the values, it will come out to be 1 minus e to the power minus lambda x. Again, you all are expected to remember the integration of e to the power cx. It is nothing but e to the power cx by c. Now let's take a look at its calculation of mean expectation x. Expectation x will be x lambda e to the power minus lambda x dx 0 to infinite. Note that we had done something called a gamma integration or a gamma integral earlier. You could directly use the result here, or you could also apply integration by parts. So if I want to apply integration by parts, let's say I can take x as the one function and lambda e to the power minus lambda x as the second function. First, I will keep x constant, integrate this, minus differentiation of x, integral of this term, and again we integrate it. You can go about that, but I will try to use gamma integral because that will be a lot more easier. See, when it is x, you need to apply integration by parts once. When you will be calculating expectation x square, you would have to apply integration by parts 2 times. Now, if it is expectation x to the power 5, you have to apply it 5 times. That will become extremely lengthy. So the shorter, more efficient way of doing this is, this comes out to be x e to the power minus lambda x dx 0 to infinite. Now, if you will remember, the formula for gamma integral, check it out. What was there? It was covered in first class or random variable? First class only, I guess. Gamma a by lambda whole to the power a. So here, again, you need to compare. When I say a or alpha, this was nothing but when x was expressed as alpha minus 1, right? Here x is to the power 1. So my alpha will be what? It shall be 2. It shall be 2 over here. You need to bring it in that form. Lambda x to the power 2 minus 1 e to the power minus lambda x dx 0 to infinite. Now this will be nothing but lambda into gamma 2 divided by lambda square. Gamma 2, again you can check out, gamma n was nothing but n minus 1 factorial. So gamma 2 is nothing but 1 factorial, which is nothing but 1. So what I'm left with is lambda into 1 factorial by lambda square, which comes out to be nothing but 1 by lambda only. So again, going forward, do keep referring to the first 4 prerequisite classes. A lot of results we would be using in this chapter as well as the later chapters. Just keep one thing in mind: when using the result for gamma integration, you need to ensure that the limits are from 0 to infinite. If that is not the case, then there is no other method apart from doing it using integration by parts. And make sure you all are comfortable performing integration by parts, because that would be required. Now we have calculated the mean of this. How to calculate median? Median is basically the point which divides data sets into two equal halves. That is, the probability of getting a value less than median is 50% and more than it is also 50%. So what you need to do is basically equate CDF to 0.5. CDF is nothing but less than equal to probability. If I equate this to 0.5, from there I will be getting the median. So let me just show you over here for completeness. I calculated mean. Now we will see how to go about calculating median as well as mode. So for median, it's straightforward. Let's say m is the median. So probability x less than m is nothing but 0.5. 1 minus e to the power minus lambda m is nothing but 0.5. And from here you will get that e to the power minus lambda m is nothing but 0.5. So minus lambda m is nothing but ln of 0.5. Now remember, what is 0.5? It's nothing but 1 by 2. Ln of 1 by 2 is nothing but minus ln 2. How do we get this? Ln half is nothing but ln 2 to the power minus 1, which comes out to be minus ln 2. So what I have is lambda m is nothing but ln 2, or my median is nothing but ln 2 by lambda. My median comes out to be nothing but ln 2 by lambda. Next, to get the mode. Now, when we used to study, let's say in summarizing data or earlier, mode was simply nothing but the data with the highest frequency. In case of continuous distribution, mode is basically that value of x which maximizes my PDF. PDF used to look in this form. It used to give us the relative likelihood. So mode is nothing but the one having the highest frequency, or here the one having the highest PDF. If I'll just take a look at this graph, say this is the graph of an exponential distribution where this is x and this is fx, then the mode is nothing but the point at which the PDF is maximized, that is here. So now to find the mode, if you would remember, to find the point of maxima or minima, we had to get the first derivative, equate that to 0. Second derivative needs to be negative in case of maxima, positive in case of minima, and in case it is 0, then it's nothing but an inflection point. Inflection point is basically the point at which the shape of the graph changes. Either it goes from convex to concave, concave to convex, anything. So here, I need to maximize PDF, right? Fx was given to be lambda e to the power minus lambda x. Take a look, then you can note it down. If I differentiate it once, this will come out to be minus lambda square minus e to the power minus lambda x, and second derivative will come out to be lambda cube e to the power minus lambda x. Now you will see that the first derivative, lambda is positive, so lambda square is always positive. E to the power minus lambda x is also always positive. First derivative is always negative. That is, it never takes the value 0. It will only take the value 0 when either lambda is 0, which cannot be the case, or x is infinite. Again, x infinite means kind of undefined only. So my first derivative is always negative. What do we understand if the first derivative of a function is always negative? It's a decreasing function. If the first derivative is always negative, it's a decreasing function. If it is always positive, it's an increasing function. Now try to understand and appreciate this. If my first derivative is negative, we have a decreasing function. So what happens in a decreasing function? As the value of x keeps on increasing, the value of the function will keep on decreasing. So when will the function take its maximum value? When x takes its lowest value. When x takes its lowest value. We have a decreasing function. As the value of x increases, fx decreases. We want the maximum value of fx. So this will correspond when x takes its lowest value, which here is nothing but 0. So here the way you need to go about is the comments, or take it down. I'll dictate it only. Write this down, or don't draw this graph, or you could draw this graph as well, just to say that this is the mode. This isn't the graph of exponential distribution. Just keep in mind, this is a random graph I have drawn. So you can write it down. The first derivative is always negative. The first derivative is always negative, implying that fx is a decreasing function of x. Full stop. Hence, fx will have its maximum value when x takes its minimum value. Which is 0 over here. So mode is 0. Now, if you would remember, for a positively skewed distribution, mean is greater than median is greater than mode. Here, what mode am I getting? 0. Right, that is the lowest. Mean is 1 by lambda. And what is median? ln2 by lambda. If you will calculate ln2, this is nothing but 0.693. ln2 is nothing but 0.693. So my mean is the highest, my median is next highest, and my mode is the lowest. And we know that, again, this will imply that my exponential distribution is nothing but a positively skewed distribution. This is one way. Alternate ways, you directly find skewness that will show that my exponential distribution is always positively skewed. As the value of lambda increases, it becomes less and less positively skewed. You can take this down. As the value of lambda increases, it becomes less skewed. And when I make this statement now, again, it is not, I would say, very technically correct as such. What I mean by this is, as you know, you will keep on increasing the value of lambda, your mean and median will come very close. And it will be tending towards what? Zero only. As you will keep on increasing your value of lambda, your mean will be tending towards zero. Your median will also be tending towards zero. Mode is always zero only. So in that sense, I can say, since these three all are coming nearer, so the graph might be less positively skewed. So this we have found out for my exponential distribution. Next, give the heading gamma distribution. So how we denote it is as x follows gamma alpha comma lambda. Again, just keep in mind, I tend to repeat alpha comma lambda. Alpha is written in this way, but I tend to write it basically over a here. A comma lambda, you can write alpha comma lambda, it's the same thing. This is actually alpha. In certain cases, it might be written in this particular form as well. So x follows gamma alpha comma lambda. Again, here both of these needs to be positive. So this is the PDF. Again, keep in mind, it's the range is again 0 to infinite. For most of the distributions, we will see that the possible values which x can take is going to be 0 to infinite. Now for CDF, no closed form exists. We were able to integrate this and get a generalized form. Here, we cannot do that. If you try to integrate this, you don't know how many times you need to apply integration by parts over here. So there is no closed form as such. You can write it as no closed form. Next, let us attempt to find its mean. It's going to be fairly straightforward. You just need to use the property of gamma integral. I can take the lambda to the power a by gamma a constant outside, and this comes out to be x to the power a, which I can write as in this form. Just take a look once. X into x to the power a minus 1 is nothing but x to the power a, which I can write as a plus 1 minus 1. Now in integral, we have nothing but a gamma integral with the parameters a plus 1 and lambda. Now gamma a plus 1 is nothing but a into gamma a into lambda to the power a whole divided by lambda to the power a plus 1 into gamma a, which on simplifying we get nothing but a by lambda or alpha by lambda. Similarly, you can go on and perform it for expectation x square x cube, so on. Its variance is given to be alpha by lambda square. Now, if you would closely observe the PDF of gamma distribution, let us try to put the value of alpha as 1. Lambda to the power 1 is lambda. Gamma 1, 0 factorial. 0 factorial is nothing but 1. X to the power 1 minus 1. X to the power 0, which becomes 1. So what we're left with is lambda e to the power minus lambda x, which was nothing but the PDF of my exponential distribution. So you can think exponential distribution to be nothing but a special case of gamma distribution where alpha takes the value 1. So you can take this down. When alpha takes the value 1, the gamma distribution gets reduced to exponential distribution. Now let us attempt to find the mode. Now just keep one property in mind which we would be using later as well. This is the PDF. Okay. One way is you go about differentiating this. Set the first derivative as 0, find out, so on. Concept is at whichever point the function fx is getting maximized or minimized, the function ln of fx will also be getting maximized or minimized at the same point. So if say fx is getting maximized at point A, the function log fx will also be getting maximized at the point A. If this is being minimized at point B, log fx will also be getting minimized at point B. The reason is that in lot of cases we'll see terms raised to the power. So differentiating this directly might become a bit cumbersome. Easier way is you take the log of it and then go about performing the differentiation. So here if I take the log, my first term will be a ln lambda. Then I will have a term a minus 1 ln x. I will have a term minus lambda x and I will have a term minus ln of gamma a. I've used the property that ln of a by b is ln a minus ln b and ln of ab is log a plus log b. So there are three terms being multiplied in numerator. All of these will be getting added up. Log of lambda to the power a is nothing but a log lambda. Log of x to the power alpha minus 1 is nothing but alpha minus 1 log x. Log of e to the power minus lambda x is nothing but minus lambda x. Again, remember that ln of e to the power x is nothing but x. And then I have gamma alpha in denominator, so minus ln of gamma alpha. Now I need to differentiate with respect to what? X. First term will be 0. Second term will be second derivative. This will come out to be minus a minus 1. Now I need to equate the first derivative to be nothing but 0. On doing that, I will get x is nothing but. Now note that this will only exist if alpha is greater than 1. Why do I say that? The random variable can take only positive values, right? The random variable can take only positive values. So its mean, median, mode, anything should be positive only. Lambda is positive, fine. When will the numerator be positive? Only if alpha is greater than 1. Right. So in case alpha is less than 1, then the mode shall be 0. Then the mode will come out to be basically 0. And other than that, if alpha is greater than 1, then the mode is given by alpha minus 1 by lambda. And since again we are stating the condition that alpha must be greater than 1, in this case the second derivative alpha minus 1, if alpha is greater than 1, this numerator will be negative, x square is always positive, so clearly the second derivative is negative. Therefore this point is nothing but my point of maximum. You can take the result. This is the mode of a gamma distribution. Do mention as well, mode is 0 when alpha is less than 1. Mode is 0 when alpha is less than 1. We will also see here, we saw that there was no closed form of the CDF function, right? So we will see if I want to calculate probabilities or anything, then how to go about it. Either you can normally integrate the PDF if you know the values of alpha and lambda, or later on we will see that we convert gamma distribution into another distribution to calculate its probabilities. No Harsh, it will be alpha minus 1 by lambda only. You are equating this as 0. X goes on the other side of numerator, lambda comes in denominator. So it will be, it's the correct form only. X is alpha minus 1 by lambda. Now if we take a look, what was the mean of gamma? Alpha by lambda. Median is, mode is alpha minus 1 by lambda. So obviously mode is always less than mean. And we will see that, or that is actually the result, that a gamma distribution is always a positively skewed distribution. As for to look at the structure of the graphs, when you will be starting with R programming, from there you can directly get the graphs. Like say for an exponential distribution, the PDF will be like this. It will always be like this. The steep might vary depending on the value of the parameter lambda. For an gamma distribution, if alpha is greater than 1, it should be something like this. And in case if alpha is less than 1, then it will again be of something of this form only, because mode is nothing but 0. So it will be of this form only. So one more thing actually I like to correct is an exponential distribution will always remain positively skewed only, because the structure will be in this form only. It will always have a mode of 0. So when I said as value of lambda increases, although mean, median, mode comes together, but still it becomes what, even if mean, median, mode are coming together, it's all nearing 0 only, so it will have a skewed graph only. So this was my gamma distribution. Next what we did was the Pareto distribution. Next I have as Pareto distribution. The way to write it is X follows Pareto. Again, the parameters are alpha comma lambda, both of them must be positive. PDF is given to be just before that, if you would remember, in discrete distributions we did that binomial is nothing but summation of independent and identically distributed Bernoulli. Same was for negative binomial and geometric. Similarly, gamma distribution is nothing but the summation of independent and identically distributed exponential variables. So again, this is something we will be dealing in chapter 3 as well when we start with generating functions. If I add, let's say, n independent and identical exponential lambda distribution, the resulting will be gamma with parameter n comma lambda. So we will be taking a look at that later. Next, Pareto distribution. Again, if you take a look, x takes the value from 0 to infinite. CDF, we do have a closed form. So the mean is lambda by alpha minus 1, and the variance is alpha lambda square by alpha minus 1 whole square, alpha minus 2. So one of you is asking is, when do we know whether the closed form exists or not? So first of all, you can give it a shot. Try to integrate the PDF and see whether you can get the CDF or not. If you can get it, closed form exists. If you're unable to get it, the closed form does not exist. And right now, for reference, for each of the distributions, I am quoting it. So you will directly find this in actual tables as well. Wherever CDF is not mentioned, it means the closed form does not exist. And the essence is you try to integrate PDF. If you are being able to bring it in a general format, fine, closed form exists. If you're not being able to do it, then the closed form will not exist. So now here, let's start to first find the CDF. Fx is integral fs ds 0 to x. So I basically need to integrate 1 by lambda plus x to the power a plus 1 lambda plus s rather 0 to x. Now if you would remember, integration of this is nothing but minus 1 by a lambda plus s to the power a 0 to x. Alpha alpha will get cancelled out and you'll be left with, when I put a lambda to the power a minus 1 by lambda plus x to the power a plus 1 by lambda to the power a, which simplifies to 1 minus lambda by lambda plus x whole to the power a. Remember that if I want to integrate 1 by x to the power a, this is nothing but similarly integration of 1 by x plus any constant, or let's say x plus b to the power a. This will be nothing but minus 1 a minus 1 x plus b to the power a minus 1. Do make yourself comfortable with all these integrations. Next, expectation x. This will be integral x fx dx 0 to infinite. Again, take a look. There are a lot of steps involved over here. I can take alpha lambda to the power alpha outside. I'll be left with x by x plus lambda to the power alpha plus 1 dx 0 to infinite. Now there are two ways to go about this. One way is, if you would remember from your school studies, we always want the denominator to have a single term. I can break this easily as 1 plus lambda by x, but I cannot break x by x plus lambda as such. So one way is I can substitute y to be x plus lambda and perform integration by substitution. Alternatively, I can do in this form. What I do is x plus lambda minus lambda. Why am I doing that? My intention is that the numerator should be independent of x, because then it will come in a form which is directly integrable. So take a look at how I'm taking it. I take this to be one term, this to be another term. So my first integral will be x plus lambda to the power alpha plus 1 dx 0 to infinite. Second term will be minus lambda integral 1 by x plus lambda will get cancelled out. So it will come in a form which is directly integrable. So this will come out to be alpha lambda to the power alpha. My first term will be integration of 1 by x plus lambda to the power alpha, and second will be integration of 1 by lambda plus x to the power alpha plus 1. Again, take a look. Alpha lambda to the power alpha. Now integration of first term is nothing but minus 1 by a minus 1 x plus lambda a minus 1 0 to infinite. Second term will be minus, will come out to be plus lambda a lambda plus x. I'll give you time to copy, just take a look right now. We got it in this form. This is directly of integrable nature. Integration of this comes out to be minus 1 by alpha minus 1 x plus lambda to the power alpha minus 1, and integration of this 1 by lambda plus x to the power alpha plus 1. A minus sign will be coming out, that will get cancelled out over here. Lambda by alpha into lambda plus x whole to the power alpha. Now a key thing here is to putting the limits. When I put infinite, I have infinite plus lambda, which is infinite. Infinite to the power something. If alpha is greater than 1, then infinite to the power any positive number is infinite, and 1 by infinite is 0. But if alpha was less than 1, then this term was becoming negative. So actually this term was going to the numerator. We have now what? Infinite and numerator. So then we will get nothing but the answer to be infinite or in a indeterminate form. So we would be assuming that alpha is greater than 1. When I assume that alpha is greater than 1, first term when I put infinite will be becoming 0. When I put 0, this will come out to be plus 1 by alpha minus 1 lambda to the power alpha minus 1. And here when I put again infinite, note that infinite plus constant, infinite to the power alpha. Alpha we know is positive. So alpha to the infinite to the power positive number, infinite. 1 by infinite is 1 by infinite, or any constant by infinite is 0. And when I put a 0, I will be getting as minus lambda by alpha lambda to the power alpha. So this, if you simplify, you will get this as 1 by alpha minus 1 lambda to the power alpha minus 1 minus 1 by alpha lambda to the power alpha minus 1. If I take 1 by lambda to the power alpha minus 1 common, I'll be getting this to be. Achha, I missed one thing. There is an alpha lambda to the power alpha outside as well. So if I multiply this, first term will come out to be lambda by alpha minus 1. Next term will come out to be just lambda. This becomes lambda minus alpha lambda plus lambda whole divided by alpha minus 1, which simplifies to nothing but lambda by alpha minus 1. And the condition comes right from here only. If alpha is greater than 1, then only the terms are coming out to be 0. So here, in case of Pareto, the mean exists only if alpha is greater than 1. So this is just mathematically, if derivation is there, you need to know where this condition is exactly coming from. Logically, we could have told Pareto is taking only positive values. Therefore, its mean must always be positive. Numerator is positive, denominator will be positive if alpha is greater than 1. Mathematically, while performing integration, this is from where we get this particular condition that alpha must be greater than 1. So keep in mind, this was one technique where I added lambda and subtracted lambda to begin with. That was the manipulation. Alternatively, just you can do integration by substitution. In case you need to calculate expectation x square or expectation x cubed, so on. Now remember one thing again, in actuarial tables, you will see that the formula for expectation x to the power k is given. For a Pareto distribution, expectation x to the power k will only exist when alpha is greater than k. Like when I found expectation x, alpha had to be greater than 1. When you'll be finding expectation x square, you will see that you'll get the condition that alpha must be greater than 2. And here also we saw when I quoted variance, alpha was greater than 2. So remember that for a Pareto distribution, expectation x to the power k will exist only if alpha is greater than k. You can take this down. For a Pareto distribution, expectation x to the power k will exist only if alpha is greater than k. So this was Pareto distribution. Next, what we will do is the Weibull distribution. Okay, we have 3-parameter Pareto as well. So let me take you all go through that as well. So here if you'll see, in the actual tables itself, page number 15. We have a Pareto distribution. It's written as 3-parameter version. The parameters are alpha, lambda, and then another additional parameter as k. Just keep in mind when k takes the value 1, the 3-parameter reduces to the 2-parameter. So the structure is given in this form: gamma of alpha plus k, lambda to the power a, x to the power k minus 1, gamma alpha, gamma k, lambda plus x, whole to the power alpha plus k. When we put k as 1, it will reduce down to nothing but the 2-parameter Pareto distribution. Its moments, variance, expectation, x to the power again is given. So this was 3-parameter Pareto. Next, again from here only, let us take a look. You can copy it down from here. We have a Weibull distribution. The way to write it is x follows Weibull c comma gamma. The parameters usually used are c and gamma. The PDF is c into gamma into x to the power gamma minus 1 into e to the power minus cx to the power gamma. Note that this gamma is basically being raised to the power x. The distribution function or CDF is nothing but 1 minus e to the power minus cx to the power gamma. And the mean is given to be gamma of 1 plus r by gamma into 1 by c to the power r by gamma. So in Weibull, we'll try to attempt how to find the distribution function. We'll see that here, if you will closely see e to the power minus cx to the power gamma. If you will be differentiating this, you will get nothing but a form in this particular format. If I differentiate e to the power minus cx to the power gamma, one term will remain same. Next, I need to differentiate what? Cx to the power gamma, which will be c into gamma into x to the power gamma minus 1, which is what we are getting over here. So for Weibull distribution, now if you can directly recognize, fine. If you can't, you need to basically make the substitution that y is nothing but e to the power minus cs to the power gamma. Either you can take this, perform integration by substitution. Directly, you can also see that this is nothing but integration of, and this will give us the required result. Could you all check if in the first class I had given beta integral as well? Prerequisite class 1, there must have been a result for beta integral as well. It's there. So what did I made you all write after Weibull today? Beta only or chi-square? Today's class, the ordering beta. Okay, so now let's take a look at the beta distribution. X follows beta, say A comma B. Now PDF is given as and here you need to keep in mind that X can take only values between 0 to 1. In all other distributions, continuous distributions we have covered so far, it was taking the value between 0 to infinite. Here it can take the value only between 0 to 1. Again, here CDF does not exist in a closed form. So if I'll take a look through the actuarial tables itself for beta distribution, you will see that its PDF is given, nothing is given for distribution function. So basically the closed form does not exist. Again, its expectation and variance is given. We will try to see if you would have guessed, if we need to find its expectation X, we'll basically need to have to use the result of beta integration. And we will attempt to do that. Along with that, also I just wanted to mention key one distribution which I missed kind of was after Weibull, we also have something called a Burr distribution. If you will look at the similarity of structure, this Burr is looking very similar to Pareto, only that X has a power of gamma. If you make gamma as 1, then you will see that this structure will simplify to nothing but a Pareto distribution only. So you will see how closely these distributions are related to each other. Later on, post this class, do take a look at this particular chart as well, page 20, which is going to basically give you the results between a lot of distributions. How we can go from one distribution to another. And this might be extremely helpful in case in an examination there is any comments based question, or they ask you from one distribution to another what's the relation, so on. So this will give you an entire picture how from one distribution we can go to another one. So do take a look at this later post we are done with this chapter. Coming back to the derivation part, expectation X, this will be integral X fx dx, limits being from 0 to 1. So I can take this outside, and inside if you will notice, I initially had x to the power a minus 1, which becomes x, which I can write in this form. And this will come out as gamma a plus 1 gamma b by gamma of in the PDF you had x to the power a minus 1. Post multiplication with x, it becomes x to the power a, which I can rewrite as x to the power a plus 1 minus 1. So this is nothing but a beta integral, result of which will be parameters are a plus 1 and b over here. So gamma a plus 1 into gamma b whole divided by gamma of a plus 1 plus b. Now I can split gamma a plus 1 as a into gamma a. I can split gamma a plus b plus 1 as a plus b into gamma a plus b. Cancelling out the common terms, I'll be left with a by a plus b. Now, if you will take again a look, try to put A and B as 1. X to the power 0, 1 minus x to the power 0, which basically becomes nothing but 1. This will be gamma A plus B, which is nothing but gamma 2, which is 1 factorial. Here I have gamma 1, which is again nothing but 1. So my PDF becomes nothing but 1, right? Which, when will I get a PDF of 1? That is in the case when, x follows uniform 0, 1. Here PDF will be nothing but 1 by b minus a, which is nothing but 1. So take this down. Beta 1 comma 1, beta 1 comma 1 is equal to uniform 0 comma 1. In notations only you can write beta 1 comma 1 is equal to uniform u 0 comma 1. Next, give the heading chi-square. Yes, so one of you is asking is the gamma integral only works when the limits are from 0 to infinite. Similarly, beta integral only works when the limits are from 0 to 1. Apart from that, anything else, you cannot use the particular result directly. So next, I have a chi-square distribution. So write down for a gamma distribution. If alpha is equal to v by 2, and lambda is equal to half, then the resulting distribution is a chi-square distribution. With v degrees of freedom, small v, with v degrees of freedom, letter v. That is, if I started from an x follows gamma, alpha comma lambda distribution. If I say a is nothing but v by 2 and lambda is nothing but half, so what I have is basically gamma v by 2 comma half, and this is nothing but a chi-square distribution. The way to write it is this chi-square with v degrees of freedom. So the parameter for a chi-square is nothing but v. So, if I take the value of alpha, say as 8, if alpha is 8 and lambda is half, means it is nothing but chi-square 4. Sorry, chi-square 16. If alpha I took what, 4 or 8? क्या बोला अभी? Alpha? चलो ठीक है. If alpha takes the value 8, my v will be nothing but 16. So gamma 8 comma half is nothing but a chi-square 16 distribution. Now the mean of chi-square is nothing but v. You can directly find from here only. Like I know the mean of gamma is what? Alpha by lambda, v by 2 divided by half, which will come out to be v only. And variance of gamma is alpha by lambda square, v by 2 divided by half whole square, which will come out to be 2v. So for a chi-square distribution, the mean is v and the variance is 2v. Again, these results are quoted in actuarial tables as well. We will also see that using another distribution called normal distribution, which we are going to do next, we can come up with a chi-square distribution as well. So we can start from one distribution and go to another distribution, So the only way to reach chi-square is not using gamma. I can also start with a normal distribution and reach towards a chi-square distribution. Again, here as we saw, chi-square is nothing but a special case of gamma distribution. It's PDF first of all. You can directly substitute these values in the PDF of a gamma distribution. You will get them. It's there in tables. As for CDF, it does not exist. Expectation X is V, variance X is 2V. Now just take this down, a particular result. If X follows gamma, alpha comma lambda, then 2 lambda X follows chi-square with 2 alpha degree of freedom. If X follows gamma, alpha comma lambda, then this particular line. Basically 2 into lambda into X. This will be following a chi-square distribution with 2 alpha or 2a degrees of freedom. And just below this, another result is all these three distributions are exactly same. Gamma 1 comma half. If you will remember, when alpha is 1, gamma is nothing but exponential only. And if my lambda is half, then I can convert it into a chi-square distribution. Alpha is 1, so my V will become as 2. So all these three are nothing but representing the same distribution. All of these have nothing but effectively the same PDF, or they are exactly the same thing. If I start from here, gamma 1 comma half. So my alpha is 1, lambda is half. So gamma follows V by 2 half. What is my V over here? As in gamma V by 2. Matlab, alpha is 1, so my V will become nothing but 2. 1 into 2. So chi-square 2. And from here also you can check. X follows gamma alpha comma lambda. Lambda is taking the value half. 2 into half, 1. Left with X. It follows chi-square 2 alpha, 2 into 1, 2. So now this was chi-square. Before proceeding further to a new distribution, now in case of we need to find probabilities, we saw that there is no closed form for the CDF of gamma distribution or even chi-square distribution. So to supplement that, in actual tables we have been given probability tables for chi-square distribution, T distribution, F distribution, as well as something called a standard normal distribution. So let me first take your what values are given in tables. Right now I'll just restrict myself to the chi-square one. So here if you'll see page number 164, probabilities for the chi-square distribution. So now here you will see values of V is given to be 1, 2, 3. You have different values of X. So what this is giving us is probability X less than equal to X. Say if I want to read this value, probability chi-square 1 is less than equal to 4 is nothing but 0.9545. Probability chi-square 1 is less than equal to 4 is nothing but 0.9545. That is the way to read this out. Now, if we go to the next page, you will have different values of B from 4 onwards till 14. Again, in the next page, you have it from 15 till 25, so on. So now, if you ever want to calculate the probability for a gamma distribution, you can convert a gamma into a chi-square. How? Using this particular result. Again, the proof of which we will cover in chapter number 3. We can use this result. If x follows gamma alpha comma lambda, 2 lambda x follows chi-square 2 alpha. And then I can use the chi-square probability tables to compute it. Clearly, alternatively, if the value of alpha is very low, you can apply first principle and integrate it as well. If the value of alpha is very low, then the number of times you need to perform integration by parts will be very less. So you can normally integrate the PDF to get the probabilities as well. So this is the way for all other distributions. You can normally integrate the PDF to get probabilities. For chi-square, you have a probability tables to refer to. Note that here, not all values of x are there. It is basically what? First value of x is 0, 0.1, 0.2, 0.3, so on. So if you have something, if you want probability chi-square is less than 0.15, so that is directly not available. So you'll have to apply what? Linear interpolation. What we did in the first class, we had applied first class, or I don't recall, in one of the prerequisite classes, we had covered linear interpolation as well. You need to apply that over here. So if I want the value of the function at 0.15, I will interpolate between 0.1 and 0.2. If I want the value of 4.27, I will interpolate between 4.2 and 4.3. So this is the technique. Next we have normal, but I don't think so we would be able to cover all of these today. So let's keep it till here only today. Next day we would be covering the normal distribution, log normal, T distribution, as well as F distribution, and then another small topic called random number simulation. We would be doing that as well. And then Poisson process also left out. So any doubts you all have with respect to today's class? Okay, no doubts then. Thanks everyone. That's all for the day.